Good afternoon. My name is Graeme Keith. I'm an independent consultant based in Copenhagen. I work with mathematical modeling applied to various business problems, strategy, risk management, portfolio analysis, decision analysis, data analytics, wherever we can use mathematical modeling to help inform decisions, particularly where those decisions involve uncertainty. And obviously the modeling that I work with generally involves uncertainty. Today, I'm going to talk about subject matter expert elicitation and two particular problems. I'll introduce the protagonists in this presentation. This is Mr. Grumpy, Mr. Happy, Mr. Brave, and Mr. Quiet. These are my four subject matter experts. And we're working on a project. A big project, has lots of phases. And I've been asking my four subject matter experts for their opinions or their estimates on what these different project phases will cost. So I say, okay, so we're coming into a project phase. Can you give us an estimate of costs for this phase? And they give me a range. I've been asking them to give me a P5 and a P95. So the bounds of the range, 90% of it's a 90% confidence interval. So what we'd like to see is that the actual costs, when we see them at the end of the project phase, 90% of the time, the actual costs will fall into that 90% confidence interval. So I asked Mr. Happy here what he thinks the cost is going to be on the next phase, and he gives me this range, that's the red. And then when the phase is finished, I say, okay, well, this was the actual cost, and then I mark that on with the blue cross. So, and we've done this, it's been a big project, we've been going for a while, so we've got 20 different assessments where they've estimated a range for what they think the cost will be, and then we've got the blue crosses marked on showing what the actuals were. And you can see that in Mr. Happy's case, it's not absolutely abundantly clear just looking from this graph, but you can see at least a few times he comes out pretty, the actual costs come out quite a lot higher than the range he's given, as we might suspect him of being a little bit optimistic here. Mr. Grumpy, on the other hand, here, his actuals come out quite a bit under his estimates here, so we maybe think he's possibly a little bit pessimistic. Mr. Brave, it's not abundantly clear. Quite a few places where he comes in quite a lot under, but a few places where he comes in over. Not very, very clear there. And Mr. Vague seems to be doing quite well in terms of getting a large number of, I think 18 or 19 in this case, of his estimates within the range. Sorry, of his actuals are coming in with the range. But then actually, when you look at these and you look at the scale here, you can see that they're fairly wide ranges. We get a slightly clearer picture if we sort of rescale. So we move the P5, the lower bound, up to the number 5, and the P95, the upper bound, up to the number 95, so that the ranges are all the same. So we're not marking percentiles, because to do that we'd have to assume a probability distribution. We're just rescaling, linear scaling, to see where people are lying. And you can see here actually, yes, Mr. Happy is his actuals are coming in quite a lot higher. Mr. Optimistic, his actuals are coming in quite a lot higher than the range. Grumpy here, quite a few of them are coming in quite a lot down on the range. Mr. Brave's ranges seem to be a little bit small, and Mr. Quiet's ranges are possibly a little bit large. And really, what we're trying to do today is to try to be a little bit more scientific, or at least a little bit more quantitative, about that kind of statement. We're basically looking at these results, eyeballing them and saying, well, he's like this, and he's like this, and he's like this. And what we'd like to do is to say, well, can we do that in a slightly more systematic way? So I have two fundamental lines of inquiry here. And the first is exactly that. How good are those assessments? Can we score them? So there's a question there of are they too optimistic? Are they too pessimistic? Are they overconfident? Are they too vague? So one question is, can we score them? Can we let them know how they're doing, and perhaps feed back a little bit to them and say, okay, look, these things are too optimistic. You need to look at your process and try and understand where you can sort of remove some of that rosiness, or maybe your ranges are too small. You need to sort of broaden the set of possibilities that you consider when you give those ranges. So can we put a number on the optimism, pessimism? Can we put a number on the overconfidence, bring the ranges in, the vagueness, pushing the ranges out? and then use that number to characterize them, to say, okay, so I, on the basis of this look back, so not just eyeballing it, but doing some sort of analysis, I can actually, what I've done here is I've said Mr. Happy, and then I've generated a bunch of happy, optimistic projections, but I'd like to be able to do it the other way around, seeing a sequence of happy, optimistic projections, eyeballing it and saying, okay, they're looking happy, optimistic, running them through the machinery, and then the machinery coming out and saying, yes, he's actually a 7 on my optimism scale, something like that. So that's the sort of thing that we're looking for in that respect. If I'm able to do that, if I'm then able to correct or calibrate my SMEs in using that methodology, is there a way that I can remove some of the remaining uncertainty, which is essentially just noise? Can I remove that by combining SME estimates? And so that's the other line of inquiry. I'm going to spend most of the time on the first one here, and only a relatively small amount of time just touching at the end, looking at this issue of SME aggregation. Now, if the issue of SME aggregation sounds familiar to you, it might be because you were up this morning at 9 o'clock watching Doug Hubbard present Franken-SME, which is Hubbard Decision Research's take on this SME aggregation problem. And actually this work that I'm doing here and that I'm presenting here is in collaboration with Hubbard Decision Research. And as when we come to the end, you'll see that what we're trying to do here is two sort of very complementary approaches, really sort of coming at the same problem from different angles, and then trying to find some sort of the mutual synergies there so that we can get something that's actually better than the sum of its parts and build an approach to these problems that has a lot of richness and a lot of different perspectives to it. So it's a great privilege, a great pleasure to work with Doug on this. We'll start with the bias scores. The starting point here is the notion of a true or faithful uncertainty distribution. Now that's maybe a little bit of an unsettling idea, but I want you to imagine that we have what I'm going to call an aliometer, after the Latin alio, which is dice. So it's a meter for measuring chance. It's a machine, and you throw in the data that you have available, and you throw in the sort of background knowledge and all the rest of it, and then it comes out with a probability distribution, and it's the correct probability distribution. It's not subject to any bias. It's not perfect. It's not going to tell you the answer because it's a probability distribution that it's coming with, but it's a correct probability distribution. Now, this is not a frequentist view of probability. Frequentists would hate this. It's not a subjective Bayesian view of probability, because subjective Bayesian is just whatever you feel is okay. It's an objective Bayesian view, and there's good pedigree for this view, but I don't want to get sidetracked into a philosophical discussion. What we're going to do is just take this notion of the chanceometer, the aliometer, and the aliometer would produce the correct uncertainty distribution for the assessment that we're looking at here and now. Now, if my SME were unbiased and able to access all of that data, and what he would do, or she would do, is he would take this distribution here, and we were asking for this 90% confidence interval. We want it to be the P5 on the low end and the P95 on the high end. So what we would do is we would just take that probability distribution, pull out the P5 and P95, and those would be the lower and upper bounds that he would give us on the range that we're doing. The problem is our SMEs are biased, and there is noise. So what happens is we take this true distribution here, the correct aliometer distribution, and then it gets distorted. It gets sort of messed around. It gets messed around by the systematic bias, the sort of systematic tendency to be over-optimistic, pessimistic, to shrink the ranges because we don't really understand the full range of possibilities, or to broaden the ranges because we just want to be on the safe side and make sure that we always land in our range. So those are the sort of systematic biases. And then there's the sort of assessment to assessment random errors that come about from a bunch of different things. Now, bias, ineptitude, whatever, distorts the SME's perception of the true uncertainty and gives us a new uncertainty, which is distorted by this transformation here. And then the numbers that we get, the actual numbers that we get in the range, those are the P5 and the P95 of this distorted distribution. So that's the basic idea here. We go from a true distribution, and then it's transformed somehow in some way both systematically and randomly, and then we end up with this bias distribution here. So what I'm going to do is I'm going to try to find a way of doing this. I'll explain how we do this later on, but I'm going to find a way of doing this that uses two numbers. I'm going to have one number that describes the amount by which we're sort of shifting the middle of the distribution. And in some cases, that will be the mean, and we'll be shifting the mean. In other cases, it'll be a little bit more subtle, but basically the idea is that we're shifting the middle of the distribution. And then I have another number that describes how much we broaden the distribution or how much we shrink the distribution. So we have the true distribution, what it ought to have been. And then if we're overconfident, we shrink the distribution. If we're underconfident or vague, we stretch the distribution out. The range becomes too wide. If we're optimistic, we shift the distribution. Well, it depends which way around the question is. So if it's something like costs, and then we're optimistic, we shift the distribution to the left, we reduce it. If it's something like a resource estimation or an estimate of profit or something like that, then optimism is obviously pushing it the other way. So we have this issue that we have to decide which way is optimistic and which way is pessimistic when we set the questions. But what I want to do is I want to take one number to describe how much we're moving the middle of the distribution. So it'd be positive for optimism, negative for pessimism, and another number that describes how much we're stretching or shrinking the range. And I've made that positive for confidence and negative for vagueness. And then what I'm going to do is I'm going to plot where I am. So I have this axis here. This is vague, wide distributions, confident, two narrow distributions. Obviously in the middle here, that's the correct, the true, the faithful uncertainty. And then on this axis here, I have optimistic, shifting it to the optimistic direction, and pessimistic, shifting it to the pessimistic direction. Again, in the middle, that would be unbiased. So this would be completely unbiased in the middle here. And then what I can do is I can just plot where I am. I can just plot these two numbers. So if I'm optimistic and a little bit confident, Nanger's to Romero, pushed over to the optimistic side, then I'd sit here. So what this does is it categorizes the subject matter expert. So this is based on a sequence. So you need a sequence of these assessments and actuals. And then on the basis of that sequence, what we like to do is place our expert on this thing and say, okay, you are being optimistic and you also live in, so you need to widen your ranges and tone down your expectations a little bit. So we start off with Mr. Grumpy here. He's pessimistic, but he's also quite confident in his pessimism. So the pessimism, now we're talking about cost, the pessimism means that he sets his ranges too high, so the distribution is shifted, and the confidence means the range is narrow. It almost looks like the range has been widened here, but that's because the narrowness of the width is relative to the mean. So if you push the mean up, then the width will naturally widen. So he's overconfident and quite sort of pessimistic in his view here. Obviously, his opposite is Mr. Happy, who combines optimism. The distribution is shifting left. He's anticipating low costs, and again, he's very confident, and it really collapses now the range here because we've both shifted the mean down and we've narrowed the range. I have Mr. Brave. Mr. Brave is just narrowing the range. He's actually pretty neutral. He's not optimistic or pessimistic. He's just pretty neutral. And Mr. Quiet actually is the Mr. Man character here. I call him Mr. Vague because he's being vague. He's pushing the ranges really wide out to the wide here. Now, when you're doing subject matter expert calibration, the sort of thing that Doug Hubbard has really sort of launched and made his thing, you're very often answering general knowledge questions to try to get people to understand the sense of what a P90, a 90% confidence interval or a 80% confidence interval feels like. So that's sort of training people's sort of probabilistic intuition for just how wide those ranges have to be in order for you to have 90 or 80% confidence of them being correct. When you're answering those sorts of general knowledge questions, and you're not there's no optimism there. I mean, no one has any skin in the game as to when Napoleon was born or how long the Fourth Road Bridge is or things like that. So the optimism, pessimism seems not to be there, and it's this sort of brave, quiet, vague, confident axis where really everything is going on. But when you're in a sort of project environment, or I did a lot of this work originally with oil and gas geologists doing resource estimations, how much oil is there in the ground, those optimism, pessimism biases, they can be very, very powerful and very strong and very large. Okay. So we can do this, and it's relatively straightforward. I mean, it's quite easy. You take a distribution, you shift its mean, you fiddle with its variance, and then you get a new distribution out. And then this issue about going from distribution to bounds and bounds back to distribution, that's all pretty trivial and pretty straightforward. The key question and the challenge and the interesting thing, where the fun begins, is when I have a sequence of assessments and actuals like these, how do I take those assessments and actuals and turn them into those two numbers, the optimism, pessimism, and the confidence, vagueness? And that's really what we're here for. That's what we're trying to figure out. Okay. So we have this notion of a true distribution, which we don't know. We don't even know what it looks like. We don't know what its parameters are. We have a bias transformation, which is pushing the mean and changing the variance. And then we have the, and we don't know what those numbers are either. That's what we're trying to find. And then we have the numbers that the SMEs have given us. So these we do have. We have the numbers that they're giving us. So we have this true distribution, it's transformed, and then we get the bias distribution. The bias distribution has been turned into bounds, and those I have. We also have the outcomes. And this is one of the key steps here, is recognizing that the outcomes, if these true distributions are true in any meaningful sense, then those outcomes must be able to think about those outcomes as a set of samples from this set of true distributions. Now, the distributions are all different. We're not in an identically distributed scenario here. We're in, every single assessment is different. All the numbers are different. But what we're doing is we're saying the actual outcomes, I take a sample from the first true distribution, then I take a sample from the second true distribution, a sample from the third distribution, and so on and so on. So these outcomes are samples from the true distribution. I don't know yet. So here's what we do. We start off by deciding what the best estimate of the form of the distribution is. Is it log normal? Is it normal? Is it beta? Is it whatever? That's the first step. So we decide on the form of the distribution, or a representation of the form of the distribution. Those forms will have parameters. It may be the mean and variance. It may be something else. Usually we can convert from the something else to mean and variance and back again, and we can convert from those parameters to bounds quite easily. So we have the true distribution with its parameters. We don't know what those parameters are yet. We don't know what those parameters are, full stop. What we then do is we then postulate a form for this transformation. As I've said, I've hinted at a number of times, really that is essentially we just add some percentage to the mean or remove some percentage to the mean, and we stretch the variance in some way. I'll often use exponentials here so that so we get sort of a nice symmetry. If we're talking about stretching a distribution, if you just multiply by a number, then vagueness corresponds to numbers from 1, which is not changing the variance at all, to as large as you like, and confidence goes from 1 and then down to 0. So all the confidence numbers are cramped between 0 and 1. All the vagueness numbers are going off forever. But if you say, okay, it's e to the whatever number it is, then you have this sort of nice symmetry between vagueness and confidence. So there's some detail around that, but essentially what we're doing is just shifting the means and expanding and contracting the variances. So we postulate this form of the bias transformation. It should be fairly simple, because what we want to be able to do is to turn it around, go backwards. And that's the trick here, is that we have these bias distributions. We don't actually have the distributions, we have the bounds. But because we know what the distribution form is, we can turn the bounds into distribution parameters. And then what we can do is we can wash the distribution parameters backwards through the bias transformation and come up with a sort of a set of candidate distributions for what the true distributions are. So what we do is we pick a delta and an epsilon. We pick these bias parameters, and we're going to look through a whole different range of different bias parameters. We'll take one of them to start with, take one of these bias parameters, and we say, okay, if these are the bias parameters, this is the bias transformation, take my bounds, turn it into parameters. I take those parameters, wash it back through the bias transformation, and then I end up with a whole bunch of candidate distributions. And then I say, how do those candidate distributions compare to the true distributions? Now, the only way I can do that is essentially by comparing the statistics predicted by the candidate distributions to the statistics of the outcomes. And that's essentially what I'm going to be doing here. So that's the basic model. That's the basic paradigm. And using this notion of the true distribution that both is connected to the bias distributions through the bias parameters here, and then it's also connected to the actual outcomes. The actual outcomes are treated as samples from these true distributions. These next two slides are going a little bit more into the mathematical detail. It's not essential to the ongoing narrative. The later stuff will make sense even if this stuff doesn't make sense to you. This is for the slightly more mathematically minded of my audience to sort of follow a little bit, get a little bit more detail, a little bit more flesh on the bones of what it is I'm actually doing here. So these distributions, these distribution forms that I'm choosing, they will very naturally be two parameter distributions, and they'll be maximum entry distributions. There'll be things like normal, log normal, beta. Actually, there'll be log normal or beta. I won't go through these in detail. You can read about it. You can pause the video and read about them. There are natural situations to use those different distributions, but you need to choose the right distribution for the situation that you're looking in. And there's this issue about if you're looking at optimism and pessimism, you need to remember which way round it is. This issue of converting bounds to parameters and parameters to bounds, that ought to be trivial. It is trivial. They're just percentiles. So, and all of these distributions have close form expressions for percentiles and inverse percentile functions. So that's fairly straightforward. As I say, the form of the bias transformation is just a shift in the mean and a multiplicative factor for the variance. And reversing those transformations should be fairly straightforward. And then the real issue comes around this whole issue of how do we make this comparison? What is the best distribution? So I can generate the candidate distributions. That's fairly straightforward. Just turn the bounds into parameters, wash it back through the bias, and have the candidate distributions. The real interesting thing is, okay, I can turn these dials, play with delta and epsilon, but what is the best fit here? What does that even mean? I mean, what is the best way of comparing a set of distributions with a set of outcomes? And there's a sort of fairly natural ways of doing this. So one way to do it was to say, okay, I want the predicted mean of all of these actuals to be the actual mean of all of these actuals. And I can do that. And that's pretty good. And it's very simple. And when you do the mathematics, you see that it's exactly what you think it's going to be. You basically just take the difference and split it up over all of the things. That's your optimism parameter. So that's relatively straightforward. That's great. So you think, well, hey, we're going to go on now and we'll look at the sample variance. So we'll look at the sample variance of the sequence, and we'll look at the sample variance predicted by the candidate distributions, and we'll set those things equal to each other. So essentially what you do is you pick delta and epsilon. You can do this because you have enough degrees of freedom that you can pick delta and epsilon so that the means match and the sample variances match. The problem is, when you get to doing that, there's two problems with sample variance. One is that it converges very slowly. So the actual sample variance isn't necessarily even very close to the predicted expected sample variance from the distribution. So that's a bit of a problem. The other problem is that even if you had enough assessments that you can make it accurate, the variance that you see in the actuals comes both from the true uncertainty, the natural uncertainty that's there, but there also comes a variance from the errors you make in assessing the averages, and you can't split that out. You can't see where that lands. So actually that method doesn't really work. There's another measure which is sort of simpler, sort of least squares method, and you can work through the mathematics of that. That again gives you the optimism pessimism parameter, very straightforward, but it doesn't really give you the confidence vagueness parameter very well, because when you're wanting to minimize the least squares error, you're just wanting to minimize the variance, and then it just says to you just have to push the variance as low as you can whenever you can, and that's not very helpful because you're actually looking for a correct variance. So that one doesn't work very well either. What I ended up using, and what I'm going to show you now, is a Bayesian approach. And the Bayesian approach is basically saying, okay, what is the probability for a given pair of bias parameters? What is the probability that I see this sequence of bounds and actuals? And then what I do is I just diddle the bias parameters until I find the maximum probability. That's my maximum likelihood estimator for the optimism, pessimism, and the confidence vagueness parameters. And that's what I'll show you here. Now that's very nice. It has a number of good features about it. It's actually, of all of them, it's actually the simplest to implement. Excuse me. It actually allows you to do some quite clever things with the noise. Now, I've been explicit about the noise. I haven't just said that every single assessment is just shifted and shrunk or grown. I've also allowed for there to be random errors in the assessment, and that's actually very important. And we'll come back to that a little bit later on. The Bayesian approach, it allows you to do something clever with the noise. It allows you to sort of ignore it for a little while and then bring it back in later. So that's very nice. But the other thing that's really, really great about the Bayesian method is that it gives you a probability distribution on the parameters. So not only are you finding out what the most likely optimism, pessimism number and vagueness confidence number is, you also have a sense of what your of how well constrained that estimate is based on the sequence that you're analyzing. Now that means that if you don't have very many assessments, you'll have quite a wide range of possibilities. Because you just don't have enough data in order to sort of narrow that down. And it could be that the deviations you're seeing are just random. Also, if you don't have a very systematic bias, then that will also mean that that there's quite a lot of uncertainty about what those bias parameters are, and that sort of comes automatically out of the wash with the Bayesian method, which is really, really nice. Okay, so what does it look like? Well, if I take Mr. Happy here and his 20 assessments, exactly these 20 assessments here, and what I'm doing is I'm wandering around, I'm changing the optimism, pessimism parameter, I'm changing the vagueness confidence parameter, and every time I change it, I calculate what's the probability of seeing this sequence, essentially. There's a little sleight of hand, which means that actually what I'm calculating is the probability of seeing this actual, given Mr. Happy's estimates and the optimism, pessimism, vagueness, confidence parameter that I'm at on the figure. So I'm just calculating it's really the probability of seeing those actuals given the bounds for these values of the bias parameters. And most of the time it's very tiny. And then around here, the probability starts rising up and I see this sort of peaked probability distribution here, and it tops out at this point here. Now, I made Mr. Happy's assessments by using the bias transformation. So what I did was I started off with a bunch of different true uncertainties. I then distorted them with using the green parameters here. So 0.1 on the pessimism, optimism, 0.5 on the vagueness confidence. The numbers aren't that important. Well, the scale isn't that important. But what I did was I took those numbers, I generated Mr. Happy's assessments. I generated the actuals from the true distributions. And then what I did is just put all the generation machinery away and then just took the bounds and the actuals and then washed them back through this machinery to find out what that machinery would predict was the number that had been used to create them in the first place. And you can see even with 20 assessments, which is really not very many at all, it gets remarkably close. I was a little bit surprised by this. I thought that I'd have to get up to sort of 50 or 100, and I'd be telling you that you needed a 50 or 100. But actually, with 20, you can do quite well, which was a very happy result indeed. So that's very nice. So we have this uncertainty distribution about where it is. We have a maximum uncertainty. This is what we would think Mr. Happy was if we didn't know what it was that we used to generate him. And we can see we're getting pretty close on that. So that's very nice. If we go up to 50, uncertainty reduces, maximum likelihood gets closer. And if we go up to 100, they're sort of sitting right on top of each other. What about Mr. Grumpy? Well, Mr. Grumpy, we know, is the sort of opposite of Mr. Happy. And his maximum likelihood is again fairly well calibrated here. It doesn't seem to matter massively if we're going optimism or optimistic or pessimistic. What about brave and vague? Can we capture those as well? Yeah, it seems that we can. So what we're seeing here, despite the fact that actually Mr. Vague is coming out low on a lot of these things, it's actually picking this out very nicely. It's actually seeing that, no, it's pretty neutral there. And actually the error that you're seeing, the reason that he's falling out of the range is not optimism, pessimism. The reason he's falling out of the range is because his ranges are too small. And then Mr. Quiet there, again, very nicely picked up. And these are all 20 assessment That one's 100. So these, for grumpy, brave, and quiet here, those are all 20 assessment analyses, which are quite nice. So we see that, yeah, Vague's doing quite well in terms of getting a large number of his actuals into the ranges, or getting a large number of his ranges around the actuals, but he's doing that by having very wide ranges. I've also done Mr. Impossible here. Mr. Impossible here has no bias, and you can see how well it does when there's no bias. It's not perfect. It's not going to land at 0, certainly not with 20 assessments. But again, you're getting pretty close, and you can see what's going on there. So that's very nice. So it's a methodology that seems to work, at least in that sense. The next step that I'm going to do together with Doug is to look at this huge database that Doug has with all of the different SME assessments. The optimism pessimism thing, I think, won't be coming out so strongly there, because these are all trivia questions that are used to set ranges, but we can at least calibrate it on the uncertainty component of it and the confidence vagueness component of it. We have a single number. We can scale these things in different ways, and I'm thinking that probably what I'll try to do is find a scale where 0 is unbiased, and then it'll be sort of a 10 would be about as bad as it ever gets and we've ever seen. And I've seen some pretty shocking biases actually. And then -10 on the other side, and then in those two directions. So essentially what we can do is we can take people and their assessments, and we can look at their assessments and say, not in a sort of judgmental, oh, you're not very good at this, you weren't concentrating in class, but more in a sort of helpful feeding back, helping them to understand where the uncertainty is coming from. Is it because you're falling out of range because you're too optimistic, or you're too pessimistic? Or are you falling out of range because your ranges are too small, or some combination of the two? And then using it to help people understand where in their process, where in their thought process and the way they think and work through these things, they can improve things to make their assessments better. The other thing we can use this for is actually just correcting calibration. So that what you can do, I mean, there's another way of doing this, which is just not to tell people what they're doing, and then just to take those numbers and then use them to correct the probabilities. And that's also a legitimate way of doing that. So that's another possibility. This whole issue of SME aggregation, what you can do is you can use this methodology to correct the SMEs in the first place, and then aggregate them afterwards. Remember, we have both bias and noise. So we use this methodology to deal with the bias, and then the methodology I'll show you in a second to deal with the noise insofar as you can with the small groups of SMEs that we tend to have. And that's what we have. That's where it is. And what I'll do now is talk a little bit about the SME aggregation, and then we'll leave it at that. Okay, so Doug, as I'm sure you know, if you've watched it at 9 o'clock this morning, he calls the methodology where he sort of bolts together bits and pieces of different SMEs assessments. He calls it Franken-SME. So it's this sort of idea of constructing the perfect creature from bits of other features. And sort of slightly tongue-in-cheek, when I started working on this methodology, which is meant to be a sort of complement to it, I called it Bride of Franken-SME. And that's what we're going to talk about here. So this is this notion where perhaps we've taken our subject matter experts and we've either calibrated them, we've trained them, we've helped them, or we've just not told them and then corrected them. Either way, we now have fairly well calibrated assessments, but we still have noise. When I say calibrated, what I mean is we've removed the bias, we've removed the systematic component of it, but we haven't necessarily removed the noise component of it. Just the fact that people just get it wrong from one thing to another. They get distracted by, not in a systematic way, but just sort of local idiosyncratic things. So we have 4 estimates now from Mr. Impossible here, who has no bias. And what we want to do is to find a way of combining those estimates to give a sort of super estimate, a Franken estimate, or whatever you want to call it, which is sort of trying to somehow remove the noise component from those different assessments. Okay, what we do here is we use exactly the same transformation as before, but now it doesn't have bias in it, just has noise in it. And what we do is we treat the biased distributions as samples from the true distribution washed through this noise generator here. Now I know what the noise is, I know what that transformation looks like, so I can do a Bayesian inversion, and I can calculate what's called a likelihood function, which says, okay, on the basis of the observations here. Now I only have the number of SMEs I have. So maybe I have 3 or 4 or 5. I have a certain number of SMEs. So I only have a small number of samples. And the samples, I'm sampling the noise here, but I can deal with that mathematically. And what I'm trying to do is to try and find out what is the true distribution that all of these SMEs are sampling from, distorted in this way. So I calculate these likelihood distributions, and then I can either take the maximum, which is what I did earlier, or I can actually take an expected value over those likelihood distributions. They're not very different. So it's just a question of preference, and actually what you're going to use it for eventually, whether you do the one or the other. And this is what it looks like. So these are the same noise parameters as I was using to generate the SME's results earlier on, and if I remove all of the bias and just use the noise parameters, this is what it looks like. You see, there's actually quite a lot of noise here. I mean, the lower bounds are fairly close to each other, but the upper bounds are all over the shop. The true distribution, the distribution that it's taken from, is the blue distribution here, and even with that sort of relatively small amount of noise here, what we're getting is really quite large discrepancies in the on the upper limit here. We've got 2 that are relatively close together and 1 that's a long way off. And then what this method does, the Brider-Frankenstein method does, is it makes a sort of combination of these things with this Bayesian inversion methodology, and it comes up with what it thinks is the best bounds as a combination of all of those other bounds here. As you can see, it's not bad. It's getting pretty close. And given that we only have 3 SMEs, so there's really not much to work with in terms of getting rid of the relatively large amount of noise. It's actually done quite a good job of reconstructing the true distribution. Now, as I say, this is exactly what Doug's doing. So Doug's doing it in quite a different way, but the problem is the same. He's saying, okay, I've got a room full of SMEs. They're all giving me different bounds. How do I combine those bounds and make a new bound, which is a sort of super bound, if you like? Now, Doug's method is empirical. So he has this enormous database of results. And his method requires that database, but he has that database. And they make sort of categorizations in a very particular and very clever way, and then you see which sort of category it falls into, and then you look at the statistics for those categories, and then that's how that works, and it works extremely well. I mean, it works very well in terms of the statistics of the combined predictions are excellent. The overall range actually seems to be reduced, which is also very good. It doesn't suffer from a lot of the artifacts that some of these other aggregation methods suffer from. So it's extremely well performing methodology. Something else that it does is it captures extra statistical effects. And what I mean by that is that when I talk a little bit more about how mine works, I'll have to confess that I have to sort of impose the nature of the uncertainty or the deviation from SME to SME. Doug doesn't have to do that. And that's very nice because it's coming from all sorts of different things. It's coming from a kind of randomness, but it's also coming from things like people just getting the wrong end of the stick or people just not understanding a question. So Doug's methodology will pick up that if somebody is just miles off everyone else, then probably they've just got the wrong end of the stick and something's gone a bit strange with it. Whereas my methodology requires that to be an outlier in a sort of fairly kind of happy-looking statistical distribution. So in that sense, Doug's has a lot more richness in the way that his methodology picks out the different combinations and the different mixtures of people agreeing with each other and not agreeing with each other. Doug's method, and they do it for, I think, 2, 3, up to 7 SMEs. So he's done this sort of categorization and shifting. It's essentially a sort of machine learning approach. And they've done that for all sorts of different combinations of all sorts of different numbers of SMEs. The Bride method is very different in its approach. It's purely statistical. There's no empiricism at all, and it doesn't require any data, which is a good thing if you don't have any data. But it's also, and it's purely statistical. It does require a single parameter. It requires you to give it a number that tells you how different your SME responses are, and obviously you can fix that from historical performance. So that's fine, and it's relatively simple to do that. Or you can use a number that somebody else has discovered from looking at things historically, and you can just try and find somebody who looks a little bit like you in terms of the problems they're looking at and use their number, and it's not massively sensitive to this number, so it's actually relatively it's okay to do that. But it's just a single number. That's it. There's no database here. It's a single number. Then you can pick it up statistically, or you can have a guess at it, or you can use somebody else's. But it's a single number, and the whole thing just runs on the basis of that number. The upshot of that, of course, is that it's not as robust as Doug's. Statistically, it doesn't do as well. And it doesn't have this feature that it's picking up these extra statistical effects. It's not a machine learning thing. It's not based on lots and lots of data. It's based on a basic understanding of the statistical dynamics of what is generating these differences in the bounds. On the other side, it's incredibly easy to implement. There's no solving in this at all. You can do this in Excel. The formulae are a little bit complicated, but you can do it in Excel very easily, and that's that. And then it's very simple. And the other thing is you can have as many SMEs as you like. There's no limit on the number of SMEs because we're not doing any sort of empirical combinations of anything. It's all just purely mathematical. So there's no limit on the number of SMEs we have. So that's very fine. What you see here, I think, is these very sort of mutually compatible, mutually reinforcing approaches. You have Doug's approach, which is based on a lot of data. It's very accurate, but requires more work and more background data. And my methodology, that's a little bit more belt and braces, but has a lot less. We'll get started with a lot less machinery, and that's very much the approach that we're using here. Is to really sort of try and find ways where we can reinforce each other and come up with a sort of toolbox of methods and techniques that we can use to get hold of this actually incredibly important issue here. I mean, we're all sitting here in this week talking about the essential role that probabilistic models have in managing uncertainty. For someone like me, that's an utter no-brainer. But it's very, very difficult to do that in the absence of lots of good quality data, unless we are able to use our subject matter expert elicitations. And we all know there are a lot of problems with those. So these approaches where we're trying to fix those problems and trying to find out with methodologies, collect the data, find ways of dealing with it, mathematical approaches that just sort of get into the sort of combinations and how these things work together to make new bounds. They're incredibly important and very powerful. Any questions, then please don't hesitate to get hold of me. I will be on for the session, so I should be answering straight away. Otherwise, get hold of me on LinkedIn, and thank you very much for your attention.